Okay, so very briefly, good morning. Thank you for coming. Today we have a talk given by Eric Gaidos, who has is very well known, I think, for the people working on exoplanet community. For those who don't know him, he has a long research history and full of big names. He made his master at Caltech and then moved to a PhD at MIT, if I remember right. Then had postdocs at positions such as JPL and other institutes. So he's now at University of Hawaii in Manoa, where he's a full professor, not only on exoplanets, in finding exoplanets, but also in characterizing. He works on the geochemistry and geophysics of planetary planets as a whole. And he has over 100 research papers on the field and a lot of interesting things to do. So I guess he would be able to give many different talks about the whole subject. Today he's going to talk about zodiacal planets in time, and I think that's it. Give you words to speak.
Thank you, Henry. Hello, everybody. I hope everybody can hear me, both here and also online. So before I begin, I first want to thank Dr. Pali for hosting me here at the Institute for Astrophysics in the Canaries. It's my first visit to the Canary Islands, and it's wonderful to be on another chain of volcanic islands with telescopes. That reminds me a little of where I'm from, which is Hawaii, but there are, of course, differences as well as similarities. Before I also start my talk, I also want to mention that I'm coming here thanks in part not just to the Institute of Astrophysics of the Canaries, but also to the Fulbright Commission, which is an exchange program between the United States and European countries. I'm a Fulbright professor at the University of Vienna, so I haven't actually traveled all the way from Hawaii. I've just traveled the relatively short distance from Vienna. And as part of a Fulbright fellowship, you have the possibility of going, sponsored by the Fulbright commissions in various countries like Spain, to come and give lectures at host institutes and talk to wonderful people like Enrique and the many people I'm meeting here at the Institute. And so I'm spending this week here thanks to these institutes, and unfortunately have to go back on Saturday, back to reality into winter of Vienna. So like you, I'm very fond of living on volcanic islands, especially at low latitude. And I'm going to talk today about the process of time, not about volcanic islands, but about planets and how time affects planets and how planets evolve. But I will use the analogy of islands because so much of the Canaries reminds me of the things that go on in Hawaii as well. And thanks to plate tectonics and volcanism, we actually are able to witness the process of the changes of islands over time. Now, like you, we have volcanic eruptions, and in fact, the Kilauea eruption that is ongoing at the moment allows us to see geology in action. But this is not always the case. Often the processes which govern the changes on these islands over time, over millions of years, are not easily witnessed in a human lifetime. Slow processes of erosion, for example, are not so obvious if you look. So we can sometimes witness the processes, but other times we just basically have to look at snapshots in time. And for example, in Hawaii, thanks to the motion of the hotspot with respect to the plate on which the volcanic islands are being formed, we can see successively older islands as we go from the big island of Hawaii, where all our telescopes are, to the northwest, and we encounter older and older islands that have formed longer and longer ago, out, in fact, to many millions of years. The island on which I live, Oahu, is about 4 million years old, and the oldest of the big Hawaiian islands, Kauai, is 7 million years old. But there are smaller and older islands in the remnants of islands that we call seamounts that stretch out about 100 million years in time. And by comparing these islands, we can see changes in both the geology, but also in terms of the biology and the habitats that have created there as the islands have eroded and soils have formed and life has evolved. So we get to witness individual processes, but we also get to see and try to infer the evolution of these abiotic and also biotic entities over time, thanks to looking at different snapshots. And that's the analogy I'd like to take now to planetary systems, because we are witness to planetary systems and the processes that cause them to change over time, but some of those processes are not very obvious. And so by looking at planetary systems at different stages in their evolution, we can hope to try to understand those processes as they change over time. Now, we can do this, of course, because when we look out in our galaxy, not all stars are the same age, obviously. They span a range in just a galactic disk of about 10 billion years. And by looking at specific spots in the sky where we've established the ages of the stars, we can look at planetary systems of those ages. And by comparing them with different times, we can try to understand how planetary systems evolve over time. So the wonderful aspect of this is that now, 20 years on into the age of planets, of exploring planets around other stars, that is exoplanets, we are able to detect enough systems where we can ask these questions and do these observations. And this is something that is a radical change in the way we've been able to do exoplanets in the last 2 decades. So here is a picture of the Pleiades, a star cluster that is approximately 125 million years old, so about the age of the Hawaiian island archipelago in totality. And if there are planets, which we presume around those stars, we're pretty sure there should be, then we can study planetary systems of 125 million years of age. And then we can compare those to planetary systems around stars of different ages. And that's a bit of the story that I want to talk to you today about, that we've started the journey on. Now, in our own solar system, of course, a planetary system which is 4.5 billion years old, we can, thanks to studies of the planets and studies of meteorites and the parent bodies of meteorites from which they come, try to infer events that happened early on as well. So we have some idea of the processes that we're looking for when we go out and look at planets around other stars. For example, we know that the moon, we're pretty sure now, moon formed from a giant impact of some larger, perhaps Mars-sized body, perhaps 50 to 100 million years after the Earth or the solar system first started forming. And this process should also occur, at least statistically, in planetary systems around other stars, and perhaps there are moons there as well. We, of course, have the process of planet formation itself, which is not well recorded in our Earth, but thanks to the small parent bodies that have survived the planet formation process itself, they record in the meteorites that we get from them those earliest stages. We might actually have planet disruption, or perhaps complete destruction. Of course, it's difficult to say there was a planet there if the planet is no longer there in our solar system, but there is some evidence in the planet Mercury, which has an overly large iron core, that there was some disruption of either Mercury itself or the bodies that went in to form Mercury, subsequent removal of the silicate or rocky mantle around that, which left a body with an overly large iron core with a silicate mantle that's relatively small. And Mercury itself is rather mysterious because it is a very small planet compared to, say, Venus and the Earth. We also see processes that were perhaps less dramatic, but nevertheless very important in terms of determining the properties of the planets, their surfaces, and whether or not they would become habitable. Atmospheres evolve over billions of years. The Earth's atmosphere is quite different from Venus, and of course there's a story to be told about Venus's proximity to the sun, perhaps the loss of water vapor from the planet, and the development of a runaway greenhouse atmosphere composed mostly of carbon dioxide. And then perhaps later on, in events which are still trying to be understood today, there could be dynamical events where planets can change their orbits slowly over time, experience resonances, for example, the proposed resonance crossing, 2-to-1 resonance crossing of Jupiter and Saturn, and the dynamical disruption which might shake loose small bodies that could crash into other planets like the Earth. So what is been known as the late heavy bombardment, that is a series of impacts on the moon that all seem to occur around 3.9 billion years ago, may be the result of slow dynamical evolution over time of the Jupiter and Saturn system, and then the effect on the other planets. So we have these dynamics: atmospheric evolution, collisions, accretion, possible disruption, that we can now start to try to understand, that may sculpt planetary systems around other stars. And this is just a time frame for the Earth-Moon system, just showing now on a logarithmic scale. So here you see 1 million year, 10 million year, 100 million years, and 1 giga-year into the history of the Earth. The various events that shape the surface of the Earth, the formation of the moon and the surface of the moon, the evolution of our atmosphere, and our propensity of our planet to be able to support life. Of course, very important. So we have in the Earth system, and thanks to the meteorites that fall in the Earth system, the ability to investigate how the Earth system will change over time, and basically the surface of the Earth will evolve. So there's a lot going on here, including, of course, as things like I mentioned, the evolution of the atmosphere, perhaps a loss of a primordial atmosphere of hydrogen, helium, and the formation of a secondary atmosphere that is outgassed from the silicate mantle, the late heavy bombardment, the formation of the oceans, the changing of the climate over time, and then, of course, life appearing on the Earth sometime before 3.8 billion years ago. But the purpose of this scale here, the choice of the logarithmic scale, is to emphasize how much interesting things, dramatic things were happening for the first 100 million years or so, perhaps a few 100 million years. And then things become relatively quiet and more slowly evolving over time. So of particular interest, if we are looking for sort of analogs of planetary systems around the stars, is those first few 100 million years of the planetary system's history. Because according to what has happened in the solar system and on the Earth, which may or may not be representative, that is an exciting time to look. But of course, we know there are planets around other stars. We know, in fact, that planets are quite common around other stars. But that's one thing to come from that statement to actually saying how those planetary systems came to be and how they've evolved over their histories, particularly those first few 100 million critical years. So this is just one of these obligatory plots to convince you, most of you don't need convincing, of just how many planets we have found and how diverse the planetary systems are in terms of their orbital period and their radius. This is a plot of just the confirmed planets that have been detected by the various techniques that we've developed to find planets around other stars, mostly by the photometric transit technique, where the planet blots out or occults a small part of the stellar disk, producing a decrease in the observed flux from the star for a period of perhaps an hour or a few hours, and thus revealing the presence of the planet and also telling us how big the planet is relative to the star. That has been a technique that has been used by the Kepler mission, the NASA Kepler mission, which is actually responsible for the large majority of the dots that you see on this plot. But if you look at the scale here, the orbital period in days, and the planet radius in units of the Jupiters, where Earth is down here at about 1/10 of a Jupiter, then you'll see that the solar system planets, which are plotted out along this scale, are actually only one small representative or not representative subsample of a much more diverse collection of planets that are represented here, and which in turn are only the portion of the period radius space which we are able to explore with our techniques at the current time. So we are filling in this diagram. And this diagram is much fuller than the planetary systems that our planetary system represents, both in terms of the size of the planets, but also the orbital period range. For example, there are planets, very abundant planets. In fact, the most abundant planets we know of are between the size of Neptune and the Earth. And yet in our solar system, there are no such objects of that size. Most of the planets that we know of orbit on periods less than about 6 months or a few months, and are at least Earth size. And there are no such objects in our solar system of that short orbital period and size. So that doesn't mean necessarily that our solar system is strange in some ways. It's just a reminder that we are really one small piece of the entire planet puzzle. And this puzzle represents an extreme diversity of planets, which probably formed in diverse environments. We see these around M-dwarf stars. We see these formed around even A stars. And presumably they have all had their diverse evolutionary histories. Like volcanic islands, the process of geologic evolution or planetary evolution is perhaps not unique, and planets can go in very different trajectories in that evolutionary path. The Canary Islands formed by very similar processes to the Hawaiian Islands, and yet there are distinct differences between the islands due to the geochemistry of the magmas and the location of where the islands are relative to the weather patterns of the Earth. So Kepler, as I said, provides us this very large sample of planets, and yet because of the choice of the Kepler field where it falls, it is not as diverse. Let me skip ahead a slide to show you. Here. So the Kepler mission, as many of you know, has been basically was pointing for several years at the same spot of the sky with what is essentially a Schmidt telescope of about 1 meter in diameter, the aperture. And this part of the sky is looking at a galactic latitude of about 13 degrees, so it is not close to but not right on the galactic plane. That choice of that place on the sky of the prime Kepler mission from 2009 to about 2013 was selected so that there would be enough target stars in the field of view of Kepler, which is about 100 square degrees, but not so many that each pixel would have too many stars and we would be confused about which star hosted which planet. So there was a balance between the confusion produced by too many targets and having enough targets to find what Kepler was looking for, which is Earth-like planets around Sun-like stars. So these two competing things drove the selection of Kepler's field. And by looking at that specific field and also having to look deep enough to find, that is faint enough to find enough planets, you ended up with a stellar population that is relatively old, probably Sun-like in terms of age, or perhaps a little older, and relatively lacking in the stars that we would be interested in observing if we're interested in the first few 100 million years of solar system history. So when we look for young stars, these young stars that have formed from giant molecular clouds, they're often still associated with their host clusters, the cluster of stars which form from those clouds, and that is actually a tried and true method to identify young stellar systems. So there are 4 known clusters in the Kepler prime field, which are listed here at the top. You have their names, you have their ages, and you have their distances. And there are some planets that have been confirmed in the Kepler prime field that are orbiting members of those clusters. So we know roughly how old those planets are. But the problem, as you see by looking at those numbers, is that the clusters are typically old, a gigayear or a few gigayears old. Therefore, in this era, perhaps where less interesting things are going on. And they're also very far away, a few kiloparsecs, and so more difficult to study. The stars are fainter. It's harder to do all the follow-up observations that you would like to do. And also, Kepler has its own magnitude limit, and it's difficult to find planets around fainter stars where your noise is going to be higher. So this has been a limit on our ability with the Kepler field, and our ability to sort of understand the relationship between age of planetary systems and their characteristics. Every cloud has a silver lining, as we say. Unexpectedly, the Kepler mission terminated after 4.5 years or so because of the failure of 2 of the reaction wheels that keep Kepler pointed at a specific spot in the sky very, very stably over long periods of time. And as a result, K2, the successor to Kepler, was born. K2 is a mission which points along the ecliptic plane. It was a clever idea by an engineer that we could use the sun as a third reaction wheel, essentially using solar radiation pressure to stabilize the spacecraft. But the 2 consequences of this are that you need to point the spacecraft only near the ecliptic plane to keep that solar radiation pressure on one side, and you have to keep pointing the spacecraft to new spots on the sky, that is in the ecliptic plane, every 3 months. So no more staring for 4 years at the same spot on the sky. So the consequence is that instead of the prime field, which is in the upper left corner of this plot of the sky, you have a series of K2 fields which have been observed or will be observed hopefully before the end of the K2 mission, when the propellant for the reaction thrusters that keeps K2 from drifting too far is exhausted. So those fields all lie along the ecliptic plane, that sinusoidal shape in this plot of in the celestial coordinate system. And thanks to the fact that the ecliptic plane crosses the galactic plane, where most young stars lie, there are groups or clusters, clouds of stars that are being or have been observed or will be observed by the K2 mission during the intervening few years. And this plot shows those clusters according to the color scale here. So some of those clusters are probably quite old, a few hundred million years at least, but some of them are 100 million years or even 10 million years or less, including some well-known ones like the Upper Scorpius cluster, the Taurus, and then there's the Hyades. So these clusters basically have been observed, or parts of them have been observed by K2, and planets, in fact, have been discovered around the stars in these clusters. So what we have lost with the end of the Kepler mission, we have gained with the advent of K2, which is just a shadow of things to come in the future of exoplanet science. So we have a rather informal group of my students, former students, and collaborators that have been pursuing the discovery of planets and characterization of confirmation and characterization of planets around young stars and clusters. We call this project ZEIT, the German word for time. It stands for the Zodiacal Exoplanets in Time, and we have confirmed and published some planets around clusters, in some of which are shown here. So I show you 4 clusters and 3 planets in those clusters. They start with names called like epic, a long name with a telephone number attached to it, a series of digits. That's the master catalog of target stars that K2 uses. And then eventually they get a name equally unexciting, like K233b or K225b or K297b. But these then represent confirmed planets that have been validated to the extent that they are acceptable, at least to peer review in the community. So the Hyades is around 600 or 650 million years old, and I've plotted this again on this time scale of the exciting things that happened in our early solar system around the early Earth, just to give you some sense of the time scale that we are probing. The analogous sequence of events may or may not be taking place in the planetary systems around these stars. That's for us to discover. But at least we have the planets of those age. Here's the Pleiades here, which is about 125 million years old. And then Upper Scorpius is on the order of a 10 or perhaps 11 million years old. There may be an age gradient across that very large star-forming region. And then the Taurus region is thought to represent or contain stars as old as 3 million years, but as young as less than 1 million years. So again, star formation is ongoing in that cloud. And I will just talk a little bit about the highlights of this. So here's a planet in the Hyades cluster around an M dwarf, a cool star that's less massive than the sun, of particular interest because it's easy to find planets around cool, low luminosity, and small, less massive stars. And those planets often orbit in something we call the habitable zone, where the surface temperatures of the planet, if it was like the Earth, we don't know that, but if it was like the Earth, then it could support liquid water. So this is a 650 million year or so old M dwarf, and it has a planet that's about the size of Neptune on it. What you're looking here on the left-hand side is a plot of a Kepler light curve, and you see this is basically a standard processed light curve that is generated by, on the Kepler images, putting a photometric aperture and summing up the total flux in there, and doing several corrections for instrument response and the effect possibly of other stars on the flux. So on the top panel you see basically that relatively uncorrected flux, and it exhibits a roughly sinusoidal pattern, which, as many of you probably have already figured out, is the rotational variability of the star imposed. The star rotates, and it has spots on it, causing the flux to vary periodically in time. The period of this is about 3.5 days or so of the star. So sorry, 2 days. 2 days. The rotational variability is not a perfect sinusoid because the spot complexes can produce the effects of complex non-sinusoidal shape, and those spots can move over time, and you can see the result of that in changes in the structure of the light curve. There are further reductions that we've used which try to detrend or remove the systematic effects of the spacecraft motion. K2 pointing is not perfect. It is not as good. The sun is not as good a reaction wheel as an actual reaction wheel. And so there's wobble of the spacecraft that ends up being producing systematic artifacts here. But as you remove those systematics, and then as you remove, on the bottom curve, the effect of the stellar variability through processes, for example, of simple processes like fitting splines, or more complex processes like doing a Gaussian process analysis, you start to see the points which initially showed to be small, the little excursions downwards, becoming more significant. And those are the points that are falling down. In fact, those are the signatures of the planet. This is an M dwarf, and the planet is relatively close in, so it crosses the disk of the star in about an hour or so. And K2 makes a measurement every 30 minutes, so there's only 2 points in the crossing. So that's why these only look isolated in pairs or isolated points, because that's all you get during one of the transits. But when you phase fold this to the period of the planet that was discovered, that period is about 3.5 days, you get a transit that looks like this. And that's the lower right-hand plot here, with the flux basically normalized to 1, showing that the dip is about 1%. And by knowing the size of the star, in this case the M dwarfs, we study them a lot and we know what their size is. We can then estimate the size of the planet. So this planet is about the size of Neptune, as I said, and it orbits on a 3.5 day orbit around the star. We have only upper limits at this point on the mass. One of the issues with looking at M dwarfs is that they're very red, and they have very relatively less flux at visible wavelengths where Doppler radial velocity measurements can vary mass. But this is being pursued with a new generation of spectrographs that can make measurements in the red or infrared. And these should be able to pin down or at least constrain the mass, if indeed it is a Neptune mass for a Neptune-sized object. That was a relatively straightforward. We found the planet, we characterized it, we are continuing to study it. Other planets have proved more difficult to figure out exactly their nature and the origin of their host star. So here is a planet that has been also validated around a star that has been now characterized. And it was originally thought to be a member of the Pleiades. So what you're looking at in the upper left-hand plot here is a plot in celestial coordinates of a system where you have color coding according to the clusters. So the Hyades is close to the Pleiades, the red stars are members of the Hyades, the blue stars are members of the Pleiades, and the arrows indicate the direction of the motion of the stars, the apparent motion of the stars on the sky, the proper motion of those two clusters. So the star in the lower right of that diagram is this epic 21036345, which we discovered has a transiting signal characteristic of a planet around. And the proper motion of this star corresponds to the proper motion of the Pleiades. And roughly, if you know something about the effective temperature of the star from its colors, you can estimate how intrinsically bright it is. And if you know the apparent magnitude, you know how far away it is. That distance corresponded approximately to the distance of the Pleiades. So various complicated algorithms have been developed to identify members of clusters, assigned a probability of 99% membership to this star. And of course, we were very happy that we would find a member of the Pleiades around this, a planet around a member of the Pleiades. This would be the first transiting planet, at least in the Pleiades system, about 125 million years old. This star is a K-dwarf, and the radius of the planet is even smaller. So you see here now on the lower right-hand side the light curve that Kepler produced. Now here the star is quite much brighter. It's a K-dwarf. It's farther than the Pleiades, but it's much more luminous. So the noise is actually much less, and you can see enormous variation, relatively speaking, due to the variability of the star, the rotational variability of the star. And when you remove that again, you can see then in the lower right-hand plot the dips that correspond to the transiting planet. So this is on an 8-day orbit, and it is what we euphemistically call a super-Earth, a planet between the size of the Earth and Neptune, about twice the radius of the Earth. And this again is something that we are following up with Doppler measurements to measure the mass. We only have the radius at this point. So we thought that this was a member of the Pleiades, a K-dwarf in the Pleiades. But as it turns out, that's probably not the case. And we've been duped. We've been fooled by the coincidence that there happens to be a relatively young star that is moving at approximately the same space motions of the Pleiades, but outside the tidal radius of the Pleiades. And I should just illustrate that going back here. That circle around the Pleiades is what we think is roughly the 13 parsec or so tidal radius of the Pleiades cluster. But you must know more about the star in order to know more about the planet. And by knowing more about the star, this told us that most likely the star is not has not a common origin with the Pleiades. Maybe there's some deeper connection just in the fact that it is in the neighborhood. But for example, if you measure the metallicity of the star, it's metal rich, about 0.3 dex. The metallicity of the Pleiades is around solar, and that effectively is a strike against this star as a member of the Pleiades. It is also relatively slowly rotating, 20 days, compared to the most slowly rotating Pleiades members, which are about 10 days. There are ones that rotate more quickly still. But that's also a strike against that. There's also, it's still young, but perhaps not as young as the Pleiades. There's also no lithium in the star. So lithium is an element that is not produced in stars, it's burned in dwarf stars like the Sun when it reaches temperatures of exceeding around 2 million Kelvin. So if you see lithium, then that means that there hasn't been enough time for the star to burn its lithium, so it must be young. This is one good indicator. And there is no lithium in the star. So here's a plot of effective temperature versus lithium abundance. And the point here that you see with the upper limit is basically our upper limit on the lithium of the star. So normally this would be a strike against the star for not being young. But in fact, because it's metal rich, this changes the structure of the interior of the star. It basically inflates the convective boundary zone. And in a complicated way, it suppresses the burning of the lithium. So these contours on here are Summers and Pincinot's calculations of the effect of metallicity on the expected lithium abundance for as zero-age main sequence stars, basically evolving to sort of something the age of the Pleiades. And what you end up with is a statement that the star could be easily the age of the Pleiades because its metallicity, its metal-rich status, has suppressed the lithium burning. So that's not a strike against the star. But on the other hand, it's not directly an indication of a young age. But our conclusion is that it's basically a star that is probably around a giga-year old, not 100 million years old, and that the star is unrelated, at least directly, to the Pleiades. Here is just a plot here showing the period of the star versus color, so effective temperature. The big red star in the upper left point is our candidate, and all the other points are Pleiades members with the membership probability color-coded. So red is very high confidence membership in the Pleiades. Now remember that, of course, it also had a high membership confidence until we looked more closely at it. But you can sort of see there this clustering between 2 and 10 days of the rotation for Pleiades members, which is clearly not including our host star. So we try to infer what is the age of the star. You can do this based on the rotation. You get about a giga-year. You can do this based on the luminosity of the star if you try to estimate how far away it is kinematically. And you get an age that could be Pleiades age, but also could be much older. So unfortunately, K-dwarfs evolve quickly enough onto the main sequence and then too slowly to tell us much about their age. And of course, astroseismology, which is this great technique to determine the ages of planets or stellar systems, is not applicable actually to stars this cool in most cases. So we've also found planets in other clusters, like the Praesepe cluster. And this cluster is approximately the age of the Hyades, perhaps a little older, 800 million years. And they're, in fact, unlike the Pleiades where we actually found none, that was the only candidate we found. In Praesepe, we came in with a much richer catch of about 6 planets or so. So our collection is expanding, and of course, we like to make plots then of those planet properties. The size, being the one that we can tell from photometry right now. We don't have masses for these things. And you can plot the size versus the host star mass of the objects. These are the color-coded objects. These are the young planets. Or versus, instead of stellar mass, you can use the irradiance that the planet experiences. And you can see, actually, that many, but not all, of the young planets are relatively large for their compared to their counterparts, which are older. The black points are the Kepler prime field planets around stars of similar characteristic. These are mostly M dwarfs and some K dwarfs, and those are older, giga-years old. So there is some suggestion that the planets around the young stars are disproportionately large, and there is a bias in the detection because it's harder to find planets around young stars for the reasons I sort of suggested there. With you have to remove the stellar variability, for example, which is more pronounced at younger ages. So this extra source of noise makes it harder to find planets, so we might be biased towards finding larger planets. Nevertheless, we should not be finding so many exceptionally large planets compared to, for example, the largest in that clump of the black points, which represent the older giga-year stars. So we just need more statistics to be able to test this. If indeed these planets are younger, are larger systematically, this would make sort of complete sense. Because for sort of super Earth to Neptune-sized planets at least, and even things as big as Saturn or Jupiter, we expect the planets to start out big. They have high entropy states from their accretion, and they cool and contract, emitting the heat that is transported through their convecting volatile envelopes that surround them. So these are some theoretical tracks now of radius of planets of different masses, experiencing different irradiances from the host star, versus time on a logarithmic scale. And the take-home message here is that they all contract, they all decrease with time. And that time scale is on the order of 100 or a few hundred million years, at least theoretically. So this would make sense. Kepler K2 has been looking at even younger systems. Now these are systems where we are now probing at the very earliest stages of planet formation. The systems still have residual material around them that is perhaps still being accreted into the planets. So this is a planet in Upper Scorpius. It's also an M dwarf, the host star. And this just again shows you the Kepler light curve with the rotational variability, then removed in the bottom panel, showing the decreases in flux due to the transit of the star. So this planet now is a little bigger than Neptune, about 5 Earth radii, and it's also with a period of about 5 days, which turns out not to be too different from the rotation period of the star, which you can see here. You can see just by eye that the transits are almost coinciding with the minima or the one cycle of the stellar rotation variability. So now we have a planet which may have just accreted or may still be accreting. This is a 10 million year old planet. And in our solar system, the planets were still doing their thing a few million to a few tens of million years in. So now we have a probe of planet formation very early in. We don't have a mass again for this. We only have the radius of the planet. But we can start to use theoretical models to try to make a statement or try to make some guesses about what the properties of this planet is like. So these are the results of what's called a planet population synthesis model. So this is semi-major axis versus planet radius. And what is going on here is that models of disks around stars are evolved into planets in all the steps that we think occur in planet formation. And those planets are then evolved over time. And the end result is a bunch of planets. And you do this for many thousands of individual systems to get a statistical collection of planets out, which you could compare with observations. The points are sort of the end state planets. The actual curves are some representative trajectories that we've sort of picked out. And the selection box is basically those objects with approximately the right size and age as our Upper Scorpius planet. And what we find from them is that basically, since we know everything about these simulated planets, we know their masses, we would predict that this object of about 5 Earth radii is about 5 to 10 Earth masses. And it is clearly a planet which has got a volatile envelope. It's not a rocky planet around it, and that envelope is still bloated, swollen from the entropy of accretion, and still cooling. But of course, there's a variety. These are the evolutionary tracks that are the planets that produce planets that are similar to our K233b, and those tracks depend on the properties of the disk, and especially the mass of the disk and the disk dissipation time, the disk that forms the planets. So we don't have a unique solution. We have many possible planets. But as we start to learn more about this individual planet or its other sistren, we'll be able to constrain, hopefully, these models. And then going back even further in time, we can look at processes involving the disk itself that may or may not be directly connected to planets. But given that the planets are forming from these disks, we would like to know everything about them. So this is, again, now K2 light curves here of stars in Upper Scorpius, and also Rho Fucus, which is nearby and perhaps a little younger, showing dips. But these dips are huge. So look at the scale here. This isn't 1% or a fraction of 1% of the flux that's dipping down. These are tens of percent, up to 30 or 40%. So, and also these dips are not always periodic. A couple cases are, but many of these dips are episodic in nature. And these have been already known about through observations by Corot and by the Spitzer satellite, and also analogous systems have been detected from the ground. But K2 is now revealing these in glorious detail, with the kind of photometry that you can only get from space, and with long, steady observations. So these dips, individual dips, some of them look a little like a transit, and clearly something is blocking the starlight, but they're too big to be a transit of a planet, and they have the wrong shape. So on the plots on the right, you can see again the real dip as the black curve, and the colored dips are the shape that you would expect from a planetary transit. So these are irregular, they're not periodic, most of them, and they're too big to be planets. These are clouds of material of some sort, structures in the disk, which we think are intercepting the star and blocking our light on a sort of regular or irregular basis. There's clearly a relationship between the disk and these dips. The infrared excess from the disk, which is the x-axis in the left-hand plot, is correlated with the depth of the disk. We don't know exactly what that means, except it has something to do with the disk. We expected that what we would see, what we were seeing, is the disks almost edge on, and we are seeing clumps of material passing, forming and passing in front of the star, obscuring our line of sight. But just to mix things up, when we actually looked at the disks with the ALMA telescope, the sub-millimeter telescope in Chile, which allows us to resolve at least the outer parts of disks, not the inner parts was responsible for the dips, but the outer parts, those disks are not in fact edge-on. So maybe there's a distortion, or maybe we're really not understanding this phenomenon as well as we could. So that's a sampling sort of going back in time, starting about 800 million years into the planet's evolutionary history, going back into basically the very beginning of a few million years. K2 is continuing to observe fields, and we're continuing to get more data. So there are Rho Fucus and Upper Scorpius is going to be observed again. And Taurus, which is a million years old, is also going to be observed as well. And so we're going to be looking not just for planets, but for these dipper stars in there. Of course, beyond K2, which will end probably sometime, if not this year, then next year for sure, there is the TESS mission. So TESS is yet again another step up in terms of coverage of the sky, because TESS will cover actually most of the sky. Sort of ironically, it won't cover the ecliptic plane. It will cover mostly the poles, and then more lightly for shorter intervals of time, similar to K2, the areas at mid-ecliptic latitudes. And it will be looking at brighter stars, and so characterization or follow-up and confirmation will be easier. It's a smaller telescope, so it's basically restricted to looking at brighter stars, but over the entire sky. And so now we have access to essentially most of the sky, including all the young clusters that might be in there, and any young stars that are just nearby. And so one of the interests of my group and the people I'm working with is identifying those young stars for TESS observations. So how do you identify young stars? One way by M dwarfs to identify very young M dwarfs is you take advantage of the fact that M dwarfs take some time to actually evolve onto the main sequence, and they remain overluminous as pre-main sequence objects for about 100 million years. And so you can look and try to identify these based on their luminosities and their effective temperatures. So of course, to get luminosities, you must know their distances. But thanks to Gaia, we will soon have the distances to all the M dwarfs that we could ever be interested in, possibly. And so this is actually a promising avenue for identification. And then, of course, as you know, stars, when they're young, rotate more quickly, they're more variable, and like the Pleiades, we can identify stars perhaps through the rotational variability, just by the TESS data or by earlier data themselves. So that's going back in time. But of course, we can take another perspective in the evolution of planetary systems if we wish, perhaps a darker perspective, if you like, of the future. The sun will evolve off the main sequence as it burns up its hydrogen, and this will have consequences for the planetary system around it, and most stars will experience this as well, perhaps with the exception of the M dwarfs, because they just last so long. So we've been interested in trying to understand the processes that influence the evolution of planetary systems beyond the main sequence. And there's a particular interest in stars beyond the main sequence by another group of people who study the light curves of stars, the astroseismologists, because they use the stellar oscillations of evolved stars to precisely characterize the parameters of these stars, their densities, and eventually their masses and ages. And there is an intersection that's interesting of stars that are big enough, evolved enough, on the red giant branch that you can do this astroseismology, but not so large that you can't detect planets, particularly giant planets around them, by the transit method. And in this intersection of these low luminosity red giant branch stars of between 3 and perhaps 8 times the size of the sun, my student, Sam Grunblatt, has been looking for planets. And we are actually finding them. They're hard to find, but they are there. So here is a recently published paper. This has now appeared in APJ, of a planet which is basically a giant planet around a star which is evolved off the main sequence. So the planet is now experiencing irradiation levels that is much higher than it experienced on the main sequence. And one consequence of this high irradiation might be the inflation of the planetary envelope, producing this inflated giant planet. We see these giant planets that appear to be inflated beyond what the radius should be based on the degeneracy, pressure, and interior structure models of these giant planets. But it's been a controversy of what causes this. Is this delayed cooling and contraction of the planets, or is it inflation by the high radiation? And here we have a planet that, for most of the main sequence lifetime of the star, experienced moderate radiation, but only recently, in the last 100 million years or so, has experienced high radiation. And it appears to be, in the upper right-hand corner, that blue cloud, slightly bigger than the planet radius that you would expect based on its mass. And if you plug in simple models of how planets might inflate if energy is added to the envelope to swell them up in the bottom right-hand corner, you get a number like 0.2 or 0.3% of the received irradiance from the star is required to inflate the planet. And that means that it is probably the result of this irradiance, and those numbers are sort of consistent with simple models of the expected inflation of the planets. As I mentioned, Gaia will allow us to identify overly luminous stars, to observe young stars. Gaia, of course, will also give us the data, the distances to these evolved stars, so that we can more precisely now measure their radii through their fluxes. And with the radii and the densities from astroseismology, we'll know their masses. And essentially from there, we know all the observables except one thing, which is the age, which we would get from, of course, the models. But now we're entering into the era of precision, ages, and characteristics of stars, and therefore the characteristics of their planets. Of course, there are missions even beyond TESS that have been proposed, like PLATO. And PLATO's prime mission is to find Earth-like planets around Sun-like stars, and also get the ages of systems at the same time they're detecting planets. But there are places and a role that PLATO could play to observe young planetary systems as well. This is what I call the Argo Navis field. Argo Navis is an extinct constellation, an ancient Greek constellation that is no longer, the nomenclature is no longer in use, but it sits down there in the southern galactic sky. And PLATO could conceivably observe this, to observe stars between the ages of 1 and 100 million years in age. So we are now collecting, I think, for the first time, these snapshots, like observing the Hawaiian archipelago or the Canarian archipelago, the sense of planets as they are observed at different points in their evolutionary stage, between 1 million years, when they perhaps have not even formed yet completely, to a few 100 billion years and beyond. And then eventually what happens to them in the far future, billions of years from now, when they evolve off, the star evolves off the main sequence and the planets experience that higher irradiation in the giant star phase. So at that point, this will give us the data to start to address these big picture questions, such as what are the major steps in planet formation and evolution? We think we know something about our solar system. How broadly do those principles apply? What are the pathways to planetary diversity? How do you get this wonderful diversity of planetary systems if they all start out as just simple disks around stars? And particularly for M-dwarfs, which I'm very interested in, and which constitute probably the majority of planets in our galaxy, because there's far more M-dwarfs than any other type of star, how do those processes affect eventually the potential for those planets to be habitable? Because if we're looking for habitable planets, M-dwarfs are not only the most numerous, they're probably the ones that are easiest to find those planets around. So I have used the archipelago to sort of use as an analogy for understanding the evolution of systems over time, including life. One analogy to the Hawaiian Islands, between the Canaries and the Hawaiian Islands, is that they are both the archipelagos that Darwin wasn't able to set foot on. Charles Darwin, who also was interested in the evolution of systems over long periods of time, never got close to the Hawaiian Islands, but he got very close to the Canarian Islands. But in fact, he anchored, the Beagle, his ship anchored off of Santa Cruz, but he could not go ashore. There was a cholera outbreak in England in 1832, and the Spanish authorities forbade the people to come ashore from the ship, which had just sailed from Portsmouth, England. And it was to his great regret that he could not visit the Canaries at the beginning of his epical 5-year voyage around the planet, which had so many consequences for science. And he regretted this greatly. And I can share that now that I know I have to leave in a couple of days, because he said, here, quote, "We have left perhaps one of the most interesting places in the world just at the moment when we were near enough for every object to create without satisfying our utmost curiosity." And he had to sail away without having to see this wonderful place. So I've gotten a little luckier than Darwin to come here, but I also share his regret of having to leave. Thank you very much, and I'll take questions.
Thank you, Eric. So there is coffee now at 11:30 at the library, so let's take a couple of questions, and then you can continue discussing with Eric in the coffee if you... Okay.
So it's about the star suspected to belong to the Pleiades. Have you explored the possibility that the star really belongs to the Hyades instead of the Pleiades?
Yeah, so the question is whether or not this star could be a member of the Hyades rather than the Pleiades. We looked at this possibility. The space motions and the metallicity are inconsistent with that. The rotation is roughly consistent with the Hyades, but the characteristics of the star are quite different than the Hyades. So this, as far as we can understand, is completely ruled out. It would have to be a member of some other class or cluster of objects that was similar in age to the Hyades, but not the Hyades itself.
In the plot of planet radius versus mass, host mass, there are a few points that belongs to the old planetary system, and there are also some data points I believe they are not plotted because in the paper they claim that it's always detected, but actually there are also transiting systems. For example, GJ436 and GJ3470. Do you have any explanation? Because they are also abnormally large compared to the cloud of old stars.
Yes. So I'm not sure I understood the first part of the second part of the question, but the first part of the system, the question was on the points that are...
Yeah, for example, M-Earth, there's one point is very large, that's GJ something.
The 3470,
also there's a Kepler,
yes,
which is also very large.
Right.
And also you can plot some other old planets onto that, which
right.
is also very large.
Right.
Do you have any explanation?
Yes, so partially. So of course, the Mirth objects were discovered by ground-based observations, and those are extremely biased towards large planets. Something like r to the sixth, to the power of r to the sixth, the bias. And therefore, it is probable that Mirth is only picking up the tip of the iceberg. What we are comparing here essentially are the Kepler-discovered planets with the other Kepler-discovered planets, K2 versus Kepler, and these other planets have been added in for the sake of completeness. So in the case of the Mirth planets, it's probably clear why these old planets seem to be large, because they can only find the large ones due to the more difficulty of finding transiting planets from the ground, the noise sources. For the Doppler, this is a bit mysterious. And again, it might have something to do with the bias, that there is a selection effect that for the Doppler based on the mass that expresses itself in the radius. There is also the potential that targets were selected based on metallicity, for example, and therefore biased the system. The process by which these stars were followed up and discovered, so 436, which transits, was discovered also by Doppler first, and then the transit was discovered. So the selection effects for the targets for radial velocities is not as uniform as, for example, Kepler. And so there's not a clear picture of what the bias actually could be in that. But that's clearly an open question. 436 is an interesting oddball.
Any other question? So if there's no more questions, so thanks Eric again, and let's go for coffee.
Thank you.